hopefully you're interested at least a little bit in either certification or constraint programming in some sense. And there'll maybe be something interesting in this talk for you. So yes, what is the problem we're interested in here? As Peter just said, one of the very nice things about CP solvers in the context of optimization is that unlike other approaches to solving hard problems, we can claim that we mathematically can get the correct answer. So that when we claim this set of constraints is unsatisfiable, or we claim this is the optimal solution with respect to some objective function, that is actually mathematically the truth. That is not a prediction, it's not a guess, it's not fancy autocomplete, it's not anything like that. So yeah, that's something we can be quite smug about, except constraint programming solvers, of course, are still software, and like all software, can indeed be prone to bugs or interference or hardware issues, or who knows what might go wrong that could lead a CP solver to get the wrong answer. So it could claim that a satisfiable problem is unsatisfiable, or it could claim this is the optimal solution when there's actually a better solution out there. Or perhaps more dangerously, it could claim this is the best solution when actually this is not an optimal solution at all. And depending on your application domain, this might not be so bad. So you might not care in some situations whether you truly got the optimal solution. You might just be looking for something that's good enough. But certainly we can think of at least some applications where you might be pretty concerned if the solver got the wrong answer. So one of the things that a different group in Glasgow works on is kidney exchange, where basically an optimization algorithm is determining who gets a kidney. And in that case, the unit of the objective function is kidneys. So in some sense, there's a kind of moral objection there to a solver getting the answer wrong and saying this is the most people we could possibly allocate kidneys to when we could get more. Also, we might be using some kind of constraint system to provide safety guarantees. We had a talk about this, I think, at NordConsNet a couple of years ago, where basically a CP type approach was being used on an app for pilots to determine whether it is safe for the flight to take off based on a whole bunch of different conditions. And again, if that reported a wrong answer for some reason, that could be potentially disastrous or at least very illegal. And in other applications, it might just be that there's a lot of money riding on the solution. So hopefully we can be convinced that at least sometimes we are pretty concerned about correctness. And so we need to think about what we can do about that. So what we obviously do already is we test our solvers very carefully for starters. But anyone that's worked on large code bases will know that testing is difficult and also is not guaranteed to catch all bugs. So even if you see a lovely screen like this, all checks have passed, you cannot be certain that there are not still bugs in your programs. Testing doesn't demonstrate the absence of errors, even if it helps you find them. Another thing you can do, of course, is run multiple solvers and check if they got the same answer. So depending, again, on your application domain, this might be something that's straightforward to do or a bit more difficult to do, but it is going to present some challenges. Indeed, in particular, if your solver is the only solver, for example, that can really practically deal with a particular type of problem, then that's going to be problematic. And also from a theoretical formal perspective, it's not impossible that multiple solvers all get the same wrong answer. So it still doesn't provide you with that strong formal guarantee if you're in a really safety critical or in a system where we need some kind of formal guarantee. What would give a formal guarantee is if we could write our solver from the ground up inside a theorem proving system like Coq or something, where it can actually spit out formally verified code that right down to the hardware level is mathematically guaranteed to produce the results that you prove in your theorem prover it is supposed to produce. As you can probably imagine, writing code in this way is extremely difficult. Basically everything is, I don't know, 10 times harder than it would have been without formal verification. And there has been research done on this in CP. There is a formally verified CP solver of sorts, but unfortunately it's pretty far away from being able to do all of the powerful sort of reasoning that we do in modern CP solving, which is kind of the main reason we want to use CP solvers, because of this powerful reasoning. So although this would be a good approach, if we get there eventually, it seems at the moment to be pretty far off. So what else is there? As was spoiled in the introduction and in the title slides, I'm here to talk about proof logging, which is an alternative approach to certifying the correctness of the output of a CP solver, or indeed any combinatorial solver. and more generally, it's a kind of certifying algorithm. So this is how this works. So normally in CP solving, we start with a description of the problem. We give it to our general purpose CP solver, and it produces some kind of answer, which we may or may not trust. But in this context, when we've got a proof logging solver, we also want to produce a proof. So this is a mathematical certificate of correctness. It should be produced line by line during the solver's execution. So this is why it's called proof logging, because it is essentially a log file in some sense, but it is a proof that the answer is correct with respect to this problem description. And then at the end of the process, the proof, the answer, and the problem description are all fed into an independent proof checking tool. So the whole philosophy of this hinges on the idea that the checker is a much simpler piece of software that we can either trust in and of itself, or perhaps it is so simple that we can write the checker in a theorem proving environment, so have a formally verified checker. And then what we have is that if we trust this proof system mathematically, and we trust the implementation of our proof checker, it should be mathematically impossible to have a correct proof of an incorrect result. So this doesn't mean our solver is always right. We've not certified the solver itself. This is why I'm being careful in these talks to say we're certifying the output of the solver. But it does mean that if it's ever wrong, we can always detect that, right? Because something will have to go wrong in the proof. We can't get an incorrect proof of a correct proof of an incorrect result. Also, this proof file is probably a useful thing to have generally for solvers. So because it is a line-by-line description, if you like, of the working that the solver took in order to reach its conclusion, it's a useful thing for auditability. It could be an interesting thing to mine for analysis to understand what your solver did, especially when you look at which bits of the proof were actually needed by the checker in the end. And also when the solver is getting the correct answer, this is a certificate that can exist essentially for all time, independent even of the solver or your testing framework or you personally. This proof exists along with the solution and the problem description to say this is the optimal solution to this set of constraints. So it's a very powerful guarantee, a very useful method, and it's something that we might like to have for CP. So that's what I'll be talking about today. I think since I've got a bit more time in this talk, I will talk first a little bit about SAT solving, because this is where proof logging sort of first took off and is why we even have the hope of being able to do this in CP, before I then go on to CP in the later part of the talk. So first of all, on a high level, what is a proof exactly? So it's a file. You can think of it basically just a text file as a log file. And on an abstract level, it derives a sequence of facts from the problem description. So each fact is written in some kind of proof language, and it's labeled with an efficiently checkable proof rule. So it's derived from the description and any previous facts. So if you trust each derivation step individually, then you should trust the whole proof. So that if you end with a derivation of a fact which represents the conclusion that the solver arrived at, so in the case of an unsatisfiability proof, we would derive a conclusion that is like trivially false. If it's an optimization proof, we'd be looking at deriving either some kind of bound on the objective function or deriving a trivially false statement from a statement that we introduced that says we must do better than this objective value somehow. And this gives us a full proof. So basically the two things we have to decide upon when we're designing a proof logging system is what is the language for expressing these facts and what are the rules that we're going to allow to derive them. So we kind of have a trade-off to make here, because on the one hand, this whole philosophy hinges on the checker being so dumb and simple that you couldn't possibly not trust it. So we want the language for derivations and the rules to be pretty small and simple and compact. But at the same time, we want basically this proof to reflect the reasoning steps that the solver actually took. So it needs to be expressive enough to actually encapsulate what the solver does in some sense. So we need it to be simple enough to check and expressive enough to actually do the logging. And that's where we've got to try and pick something in a nice middle ground. And the SAT solvers so far are the big success story here. So I'll assume everyone's familiar with propositional satisfiability in some sense. Yeah, so we have formulas in conjunctive normal form, and we're asking the question, is it satisfiable? So this is not in itself an optimization problem, of course, but it can be adapted with a max SAT variant. But certainly now, as standard, SAT solvers pretty much universally produce unsatisfiability proofs when they decide that the input CNF is unsatisfiable. And this has even got some attention in like non-academic media even. So it's a pretty well accepted fact now that SAT solvers can do these sorts of mathematical proofs and be certifiably correct when they claim a problem is unsatisfiable. Incidentally, of course, if the problem is satisfiable, we don't really need a proof because the solution that you witness really is the proof, and you should be able to check that pretty easily. So yeah, SAT solvers are unreasonably good at solving these sorts of problems. They do various things, search and unit propagation and conflict-driven clause learning, but yet the community as a whole has managed to coalesce on a simple, efficiently checkable proof system in order to get this out. So what do SAT solver proofs look like? So if you've never seen one before, this is what it looks like. It's a, it's a big old list of numbers, but actually what these are, of course, is deriving clauses from your input formula, which is clauses. So this is just a compact representation of a clause. So each number represents the literal, and the minus sign represents the negation of the literal. And it's very natural that the input language and the derivation language here would do the same. So we're expressing all the facts that we learn as clauses and deriving them via some proof rules. Except I said before, everything would be labeled with a proof rule, and here, well, there's these D statements, which are just deletion lines. These are bookkeeping essentially. But other than that, there's no rule labels. These are literally just stating the clauses. And that's because in SAT solver proofs, there is actually only one rule. And everything that you write out is guaranteed to follow by this one rule. And in modern SAT solving, this is called the RAT rule, which is a bit of, not the greatest name, I don't think, but that's what they've settled upon. I won't talk about the RAT rule. I'll instead talk about a slightly simpler version of the same rule, which is called the RUP rule. And this was really the fundamental thing that got proof logging started in any sort of efficient, checkable way for SAT solvers. And this is, I think, the only rule I'll talk about in any great detail in this talk, because I think it gives you the best impression of what sort of proof rules we deal with in proof logging versus if you've seen proofs in other systems like theorem proving systems or just pen and paper proofs. This kind of gives you an idea of what's going on here. So the RUP rule is a rule that allows you to introduce a clause from a formula. The formula is the input formula plus any clauses you've already derived in the proof. And what it says is we can derive this clause from the input formula if taking the negation of the clause, adding it to the original formula, and running unit propagation results in an obvious contradiction. So if anyone's not happy with unit propagation, it's just constraint propagation on clauses. It's just setting any literals that simply have to be true in order to satisfy the formula, and then repeating that process until we either reach a fixed point or a contradiction. So this is RUP, which stands, of course, for reverse unit propagation, because we're taking the negation of the constraint and then unit propagating. And it's relatively straightforward to see why this rule is sound. If we have derived the statement false from the input formula, then this is the same basically as saying that F and not C is always false, which is the same as saying that the negation of this, not F or C, is always true. This is just flipping around logical symbols, which of course logically is the implication, because we know that not F or C is the same thing as F implies C. So specifically, this means that any solution to F will also be a solution to C. So adding C to F can't possibly change the set of satisfying solutions to the formula. So what that means in the end is that if we derive a sequence of clauses and they all happen to be RUP clauses, then if we derive the empty clause, so the clause that is trivially false at the end, then we have essentially proved that the original formula is unsatisfiable because it implies a contradiction. So this is actually a proof system that can be complete in and of itself, which is kind of useful. And I'm going to show you just in 1 second what we can do to proof log one of the most fundamental algorithms in SAT solving, which is the DPLL algorithm. I put this in just as a thing for later. So we talk about RUP as reverse unit propagation. There's another way to think about RUP, which is basically just any statement which is sufficiently obvious for the verifier in order for us to introduce it in the proof. So if we equip our verifier with some kind of reasoning procedure. In this case, it is unit propagation, but in principle, it could be any reasoning procedure that we just trust in itself. Then we can use RUP in a more general sense to mean things that are obvious enough for us. And when we get onto our more complicated proof systems later, that will be something that we do. So DPLL, you're possibly familiar with in SAT solving. It's kind of one of the most fundamental algorithms for solving these sorts of problems. It's very much like your standard constraint programming algorithms. So we'll start with our CNF formula. We will make some decisions. We will unit propagate until we can't unit propagate anymore. And then we'll make more decisions and repeat that until we either discover a contradiction. So, and have to backtrack or find a satisfying assignment, of course. So what we're going to do in order to add proof logging to this algorithm is anytime we backtrack, we're going to output a reverse unit propagation statement that is the negation of the sequence of guesses that led us to have to backtrack at this point. So, for example, if we guess x is equal to 0, then we would unit propagate to simplify the formula. So we get rid of x here, get rid of x here, get rid of these two clauses with not x, because these are trivially satisfied. And now there's nothing more we can propagate. Now we'll guess y is equal to 0. And again, we can get rid of some other stuff to simplify the formula down. And now u is on its own. So that must be 1. So again, we propagate. And now we've reached a point where we have p and not p. So this is a point where the SAT solver running DPLL would want to backtrack. So in this point, at the proof, we will output a reverse unit propagation statement that is the negation of the sequence of guesses. So we guessed x is 0 and y is 0. That's effectively guessing not x and not y. So the negation of that is x or y. So this is RUP. And the reason it is RUP, of course, is because taking the negation of this is not x and not y, which by the very virtue of the way we landed at this point has to unit propagate to contradiction. So this is certainly sound to introduce in the proof with respect to our original clause. Okay, so we backtrack. We're back to making a decision on y. We only have one other choice. Let's guess y is equal to 1. Okay, so now we can get rid of these clauses and we discover another contradiction, z and not z. Okay, so again, now we're backtracking. So we should output a reverse unit propagation statement. And this time the sequence of guesses was not x and y. So the negation of that is x or not y. This is fine. Okay, now we've got no more ways to set y. So we backtrack all the way back to x. And because we're backtracking, we need to output a reverse unit propagation statement again. So this is slightly different because this would not have been RUP on the original clauses because we needed to do some search in order to figure this out. But because we've been essentially maintaining an invariant in the proof log, which is anything that's known to the SAT solver is also known to the proof verifier when reading the corresponding point in the proof. So when we reverse unit propagate this x on its own, it's going to contradict the x or y and the x or not y when you run unit propagation, including the clauses that you've already logged in the proof. So this will be RUP. And in fact, no matter how long we continued this search tree, providing we're doing everything legitimately, all of these learned no goods essentially will be RUP. So to finish off the proof, we now guess x is equal to 1, simplify again, and we have z and not z. So we would output not x. And notice we've now logged x and not x in the proof. So we can now RUP the empty clause, which is essentially saying, given everything that I've logged so far, you can now unit propagate to discover contradiction. So this is actually a complete unsatisfiability proof for this small CNF example that a SAT solver running DPLL would be able to output. And what's really nice about this is if you were a solver author, you wouldn't necessarily have to know how the RUP rule worked or why the soundness of the proof system is working, although you can kind of clearly see why this will always work. Not too difficult to generalize it. But as a proof system creator, I can just tell you, whenever you backtrack, output the learn no good and claim that it's RUP, and you're done. So this is essentially why proof logging has been so successful in SAT solving. So obviously, modern SAT solvers don't do DPLL so much anymore. They do the much more effective CDCL, conflict-driven clause learning. And I won't go into detail about why proof logging works for this. But basically, the developers of proof logging systems were able to say, just write out every conflict clause you learn when you learn it, and it will be RUP. And this is great. Basically, the SAT solver people were able to just effectively add in a patch to their solver. They just printed out clauses at a particular point, and suddenly they've got unsatisfiability proofs and they've got proof logging. And this is really taken off. So what this means effectively is that SAT solvers produce unsat proofs as standard, like I say, and that wrong answers are mostly a thing of the past. Like in the SAT competition, you don't see SAT solvers reporting unsat problem as satisfiable or vice versa, in the way that in the mini-zig challenge, you perhaps see solvers reporting on wrong answers from time to time. And also, like I reported with this media output, that SAT solvers are kind of viewed a bit differently now, in that they are seen as theorem provers. And if a SAT solver is able to establish some mathematical result by doing a whole lot of very complicated search, and it produces a proof, like mathematicians are actually viewing this as a proof of that result. So this is why Marijn Hoyle has been viewed as settling some relatively significant mathematical conjectures, essentially by running his very powerful SAT solvers, which are very well engineered, and getting it to produce proofs in his proof system, which he then verifies. Not all mathematicians are on board with this as a way of doing things, but it is actually a very interesting capability that is only possible if you have a proof logging solver. So us as CP people will look at this and we're probably pretty jealous because there's no theoretical reason why we couldn't also be doing this. Like just like SAT solvers, we are also running exact algorithms with exhaustive search a lot of the time. So in the spirit of laziness, we can probably just say, well, can we just steal this research and start using it immediately in CP? And there's some difficulties which we have to get by. So first of all, as I'm sure everyone is aware, the input language for constraint programming solvers is quite a lot more complicated than CNF. In fact, this is the whole, again, one of the whole reasons to use CP. So we have to somehow deal with getting a very simple checker to understand this much higher level proof format, input format in some sense. Another difficulty is that, well, SAT solvers are mostly focused on very efficient search and learning from failure. CP solvers, although they do this as well, also have very complicated reasoning algorithms that can rely on all kinds of fundamental properties of graphs, of network flow, of basically anything you like, you can throw together in your constraint toolkit. So it's not so clear if we could have something like the RUP rule, where basically just any inference that a propagator makes is guaranteed to be RUP, and we just write out everything in the proof, because somehow that would require the checker to be as smart as the CP solver, which is the very thing that we're sort of not trusting in this sense. And then finally, of course, of most interest from an optimist perspective is that CP solvers do optimization as well. So we need to think about how we deal natively with proofs of optimality. Obviously, the RUP proof system and the SAT proof systems that I showed you before are really focused on unsatisfiability proofs. So I'll leave this surprising and slightly controversial claim here. So this is the point in the talk where I move from just talking about proof logging generally to talking about specifically what I work on with various collaborators in Glasgow. But this is the claim we make. We reckon that by switching just from clauses to 0-1 integer linear inequalities as our proof language, we can do pretty much everything that we want to do in CP. So this is 0-1 integer linear inequalities. This is well known as pseudo-Boolean constraints. So essentially, if you're comfortable with 0-1 ILPs, you can just think of them as that, except we're going to use the same literal notation that we use in SAT. And this is perfectly fine because not x is just the same as 1 minus x. So we could substitute this in and get native 0-1 integer linear inequalities as well. So we're going to use a similar proof system. We're going to have a slightly expanded set of rules, but we're not going to go as far as to say that we need an inference rule for every constraint or something like that. We're still going to keep things in a relatively low level proof system. So this is the slightly controversial claim. And so I'll head this off by starting with the main downside of this before I then talk about the reasons that this is a good idea or why we think this is a good idea. So in order to use a proof system based on, well, basically anything more low level than what you're starting with, we can't just use this basic proof logging idea exactly as it is, because this problem description will not be written in a language that the proof checker understands. So we say that you have to add just one more trusted component to this system. We need to encode the problem description in such a way that the proof checker can understand it. So this might be ringing some alarm bells immediately, because wait a second, encodings are pretty complicated. And certainly if you've ever encoded a problem to SAT, doing reformulations, doing unifications, doing all kinds of crazy things, you might even be doing symmetry breaking. This is definitely should not be a trusted component of the system. And what we're going to argue is that because we're using this encoding just purely for the proof checker to understand what the problem is and not using it for solving, a lot of these problems go away. So it's not completely unreasonable to ask that we trust the encoding. In a sense, we're using a similar sort of logic as we're using to trust the proof checker, in that this encoder is simple enough that we just check it, that we just trust it in and of itself, or perhaps we can eventually write a formally verified encoder for the problem, so that we have a strong guarantee that the PB problem, the 0-1 ILP, if you like, that the checker is looking at really does represent the same problem. Now, again, if you think this is too much of a stretch, that's probably fair, and this is one of the things that we're thinking about in regard to this research. But if you can grant me this just for now, and say, yes, okay, I'm happy to trust a PB encoding, then we get a lot of really powerful things. And the biggest thing is being able to use this pseudo-Boolean proof system, the very PB proof system. This is maybe not the best name for this thing. This started out as the name of the tool for checking the proof system, and it's kind of just become the name of the proof system. But what is very PB as a proof system and as a language for expressing facts to derive things in? It is a pseudo-Boolean proof language. That's what the PB stands for. So it derives these 0-1 integer linear inequalities from a 0-1 integer linear description of the problem. It's based on cutting planes with some additional strengthening rules. So if you're familiar with the cutting planes method for solving integer linear programs, this is not exactly the same thing, but it's pretty heavily inspired by these cutting planes rules that you would use in solving ILPs. And the additional rules bring it up to a level of strength that basically means, from a proof complexity perspective, it is as strong as any proof system that you could hope for from a theoretical perspective. It does have, as I said, a working proof checker implementation with a formally verified verifier, which is an important part of this, of course. And it has already been used for certifying combinatorial solving in a wide range of combinatorial solving paradigms. So even though it uses PB constraints as its proof language, it's not specifically designed for certifying PB solvers. It is designed to be a general purpose proof language, and indeed has optimization built natively into it. So that's why it's able to certify MaxSat, as well as graph algorithms, and now CP. So the very PB, it's got a lot of people working on it in different parts of the world, different groups dealing with different certification for different sorts of algorithms. And we were having monthly meetings just to talk about why very PB is the best thing ever and is the solution to all of the world's problems. It's only slightly occult at this point, but we do actually think at Glasgow that genuinely this is a very promising direction for adding proof logging to CP. So I'll try and convince you of that in the next couple of slides with kind of two main reasons. So first of all, pseudo-Boolean constraints are possibly a bit more expressive than you think, especially when you free yourself from the assumption that this needs to be a good encoding for solving, because all we're requiring is obvious correspondence with the original problem. So I'll use this basic form in the very PB checker. Everything has to be a greater than or equal to constraint. Like I said before, bar over the x just means not x, 1 minus x. And if we had equality constraints or less than constraints, it's very easy to reformulate this so that everything is greater than or equal to. We can always negate this as well by putting minus in front of everything and then adding 1 to the other side. That's just encoding less than. So if this is a greater than constraint, we can also encode the negation of that. So the first thing that's kind of powerful that we can do is that we can always natively reify PB constraints within the proof system. So if you're used to writing ILP encodings, this isn't too hard to see. You might have heard of big M. I think this is a term that people use in linear relaxations, but it's a similar sort of thing. If we want to write down that some literal y implies a PB constraint, then we just put a large enough coefficient in front of the negation of y and add that. And what that means is if y is ever false, then the constraint will be trivially satisfied because m is so big. But if y is true, that term disappears, and now we have to satisfy the other part of the constraint. So this is, of course, an implication. We can also, since we can negate constraints and we can express reifications, we can also express if and only if double reifications, if you like. And this is extremely powerful for modeling because we can now essentially set up a literal that has the meaning of this PB constraint in and of itself. So we could then use this literal y to mean c in other parts of our model. So this is pretty useful. This is the less obvious part because you would almost never want to do this in actual modeling for PB solving. But we can essentially just squint and pretend that we have finite domain variables in PB by simply replacing any instance where we would want to use a finite domain variable with this exponential sum that evaluates effectively a bit binary representation of that variable's value. So because this is just a linear form, you can substitute this anywhere into a PB constraint and then just pretend this collection of variables is a finite domain variable in itself. And this means we can then mix representations. So we have things like the order encoding and the one-hot encoding and various ways of encoding constraints. And we can use this all together by just mixing. So we treat the binary encoding of the variable as the canonical definition of the variable. And then we define things like, say, x is greater than or equal to k, if and only if the bits of the x that we're treating as the canonical x are greater than or equal to k. And we can define equality like this. And the great thing is, you can look at this and go, this probably isn't great. This won't propagate things. This will be difficult for solving. I don't want to be branching on these bit variables. Doesn't matter. We're only using this to represent the problem for the proof checker and not for solving. So then once we've got all of this apparatus in place, it's actually very easy to pretty much directly represent pretty much any CP constraints that we've come across as PB encodings. And so far, we've been arguing that it's relatively straightforward to say that this PB encoding does represent this CP constraints and that we don't need to worry about not trusting that. So for example, here would be an encoding of a not equals constraint, x not equal to y. We would introduce an auxiliary variable f and then say f implies that the bits of x are greater than the bits of y, or not f implies the bits of y are greater than the bits of x. And hopefully you can look at that and go, yeah, that means not equals without worrying too much about it. Again, if you don't trust that, that's maybe okay, but that's what we're going for. Obviously, linear constraints are, you can just do this directly in the system. You just substitute in the bit strings and you don't need to do anything else. So encoding linear constraints like this is a real research task in SAT solving, but for this sort of thing, it's completely trivial. And we can also encode the constraints that don't look like linear forms at all most of the time, just by thinking about what they would mean in terms of PBs. So for example, for the all different constraints, if we can introduce all of these 0, 1 literals that say xi is equal to v, meaning that the ith x variable takes the value v, then we can essentially just have a set of sums over all of the values that says that most one variable takes this value for each of the values. And again, you can think about that for a little bit and realize that that is the same thing as the all different constraint. So I claim that for all other constraints, this is relatively straightforward as well, although there are some that are certainly more tricky than others. But certainly pseudoboolean constraints are an expressive way to write down a representation of the CP proof log, CP problem, and also use in the proof log facts about CP variables relatively straightforwardly. So the second reason pseudoboolean proofs are a good idea is, like I say, they're associated with this very powerful proof system, the cutting planes proof system, which is sounding complete in and of itself. And there's various proof complexity results that shows for certain situations, most notably for the pigeonhole principle type proofs, that this can be exponentially shorter for producing proofs than, say, a resolution-based proof system, if you know about this. So cutting planes rules are as follows. It's not really important to understand exactly what the rules are right here, but essentially we can always introduce as an axiom that any 0, 1 variable is in fact greater than or equal to 0. That makes perfect sense. We can take linear combinations of PB constraints, which probably also makes sense. And we can divide through by a constant and round up, which is maybe less obviously correct from a soundness point of view, although if you are comfortable with Gomery cuts and this sort of thing, then you'll maybe be able to convince yourself that this is a sound proof rule. And together, these are actually complete. So in theory, we can prove anything using cutting planes. Although in practice, in very PB specifically, in order to make our lives easier, we have some additional rules in order to make proofs shorter and to make them easier to output. So going back to what I talked about quite a while back, we also have a RUP rule in very PB. We stole the name from stat proof logging, although it's not exactly the same thing because, of course, we now have a pseudo-Boolean generalization of unit propagation, which again is basically just propagating over the set of PB constraints that we have in the proof and in the model and seeing if we discover a trivial contradiction. So this actually encompasses unit propagation when all the constraints represent clauses. And for a CP person, it's basically bounds consistency. So we could call it reverse bounds consistency if we want, or come up with a better name. But we're sticking with RUP because stat people know what RUP means. And we've kind of got used to this terminology that RUP just means this is sufficiently obvious that we don't need a cutting planes derivation or anything else to write it out. So for example, if we defined our literals like I showed you previously, then a fact like this would be RUP. So this is saying the variable x is greater than 6 implies that that same variable is greater than 3. It's just obvious. And it's maybe from a propagation perspective, you'd have to work through exactly what gets activated and why the bit representations kind of cancel each other out. But once you know that these sorts of facts are obvious, you can just write them out in your proof without having to worry about them, which is pretty useful. Another rule I'm not going to go into in any great amount of detail is called the redundance-based strengthening rule, which is an extremely powerful rule, but all we're going to use it for in this context, and really all that we do use it for in CP proof logging so far, is to introduce fresh variables in the proof. So these literals that describe conditions about the integer variables, we don't necessarily want to put them all up front in our model. So we can just do red and introduce them with their double reified definition in the proof log if we want. And this will always be sound, providing this variable that we're introducing has not appeared anywhere yet in the proof. So from a proof complexity standpoint, this is what they call an extension rule, which extremely increases the power of the proof system. And it's also just extremely convenient from our point of view, because it means we can talk about specific conditions on variables on the fly in the proof without having to first define an entire order encoding for potentially a very, very large domain. We can use the bit encoding, which, say what you like about it, is at least pretty compact. Finally, since optimization is one of the things of interest here, like I say, very PB can deal natively with optimization proofs. And the way it does this is through a special rule called SOLI, which is basically check a solution against your PB model. And if it propagates to a complete solution, then add a constraint that represents improving the objective function. So if we specify an objective function alongside the PB model, then we can introduce SOLI. Say, for example, we witness on x equal 1, y equal 2. Imagine there's just two variables and that this propagates to solution and that we're maximizing y. Because we've witnessed that y is equal to 2, then the checker would just automatically introduce the constraint y is greater than 3 in terms of the, assuming that we have represented our objective function in terms of this bit string. And this means that optimization proofs just boil down to unsatisfiability proofs all of a sudden, because all we need to do now to prove optimality is derive contradiction from this constraint that we just introduced. So after the last SOLI line, we're now basically just in an unsatisfiability proof. And this reflects what CP solvers do and lots of other solvers in various paradigms as a kind of branch and bound sort of search. So this is good. We've got various proof rules and we've got our language for expressing constraints. So I think we've got enough now to talk about how we would actually do proof logging for CP. And we'll start by saying, imagine that we have a CP solver that does only backtracking. Well, essentially, it's just a similar thing as DPLL. in this case. So every time we backtrack, we're going to output a RUP statement that is the negation of the sequence of guesses that led us to have to backtrack, except the guesses are now encoded using these reified PB literals instead of as directly 0, 1 variables in the formula. So for example, here we guessed x0 is 1, x1 is 1, x2 is 1. So we would write in our proof RUP x0 is 1, x1 is 1, or x2 is 1. At least one of them must be false. So this is the exact same thing as we were doing before, except that we actually have to introduce these, which we can either have as part of the model if we already use them, or we would use the redundant space strengthening rule. So we kind of get a similar thing happening where we're introducing these rules whenever we backtrack, and what that's going to end, I'll just speed this up, it's a bit of a long thing, end up with is a complete proof that essentially describes the solver's backtracking search tree in exactly the same way it did for the DPLL proof. One of the cool things about this, I suppose, is that if you were designing a proof logging system just from the beginning, you might assume that you need some kind of branching rule in the proof system, since solvers are doing branching. But actually, the sequence of learned no-goods, if you like, encodes all of the branching information into the proof without you having to do any actual branching. So this is great. And this would work. This would be absolutely fine if all the solver did was backtracking search, because essentially these must be RUP on the constraint model if we defined a faithful model, because by the very definition of contradicting a constraint, these would be immediately contradictory in the model once you reverse unit propagate them. So this would be fine, except of course CP solvers do not just do backtracking search. And just because we guessed these three things and then discovered a contradiction does not at all mean that we actually directly contradicted a constraint with a complete assignment. We might have a very smart constraint propagation algorithm that did a whole bunch of stuff to figure out that we can backtrack early. So how do we have to deal with this is we need to log more things in the proof. So in between all of these RUP steps, we need to put in statements such that this invariant is preserved, that anything that the verifier knows, everything that the solver knows is also known to the verifier on reverse unit propagation of the backtrack constraint. So this turns out to be quite a strong overlap with the lazy clause generation paradigm, because it turns out exactly what we need here are the same justifications, if you like, that the explaining lazy clause generation propagators generate. And this is partly just to do with the way the RUP rule works. So if we guess, say, x0 is 1, and then we propagate to remove 2 from the domain of x1, then this needs to be available in the proof somehow as a justification of the form x0 is 1 implies x1 is not 2. So this is the same as these sorts of justifications, except this might not be RUP, because who knows how the propagator arrived at this inference. We actually have to derive this in the proof somehow. But once this is here in the proof, when we're reverse unit propagating on our backtrack constraints, then propagating this x0 equal 1 will then force this x1 not equal to 2 to propagate, which will allow the complete proof to still be a complete proof in the sense that it was before. So we've reduced the problem to the problem of justifying all the propagators by outputting these explanations. And this is where the kind of strength of all the other PB proof rules in aside to RUP actually becomes pretty useful. So it turns out, yeah, this is the form of the justifications in general. We need to have some sort of reason. It doesn't need to be everything that we guessed at that point. It could be some subset that encodes the domains that are actually needed for that propagation, but that is all we need. So some constraints are really easy to do this for. And this is part of the big strength of using PB encodings. So for example, the not equals constraint that I used before, this is one RUP step to justify this, which is really pretty useful. So say, for example, we have x in 1 to 15 and y in just 5, and x is not equal to y, hence x is certainly not 5. Any not equals propagator should be able to infer that. So we need to write in our proof some kind of justification of y equals 5 implies x is not 5. And all we need to do essentially is make sure all these literals are introduced with the correct reification on the bit encoding. So in the worst case, this will be 6 double reified constraints for both x and y, which looks bad, although at the same time, we only need to do this once for each of these kind of literals. So potentially these are all introduced already in our proof log, depending on what we're doing. But once we have all of these here, and this isn't immediately obvious to see, but we can prove this in general, this will always be RUP. So just propagating this thing on all of these literal definitions will give you contradiction. And so we can justify not equals constraints by basically telling any solver author, if you've got a not equals constraint, you just need to write a RUP step for your explanations that you produce. And if you're already working in an explaining solver, this is even easier because you already have the explanations. So that's pretty good. Some constraints are a little bit more complicated. I'm just going to show you this just to give you a flavor of the kinds of harder arguments we can do in PB. I'm not expecting this to make a full amount of sense. But say, for example, we had a situation like this with the domains of V, W, X, Y, and Z, and we're imagining these are involved in all different constraints. There's nothing that immediately contradicts all different there because none of the variables are even set, but a good all different propagator should be able to discover contradiction immediately. Can anyone tell me why? It's not Peter, because he answered this last time. Yeah.
You have five different possible values, 5 different variables, and only V can be 4 alpha.
Okay, so I think that's the negation of the same thing that I was going to say, which or is the complement of it, which is, I think what you mean then is that there are 4 variables here with only 3 possible values between them. Yeah, it's another way to put it. This is the Hall set. So the all different propagator can do this kind of reasoning. Of course, it does various complicated things to discover the Hall sets, but once it sees it, it can justify this in the proof as follows. So yeah, we identify that, so we know what that is. So this is the justification procedure. We're going to have a reason R, which is a conjunction of literals sufficient to encode these particular domain changes. So these would be potentially W is less than 4, X is greater than 1, and less than 4. And then for each of these reasons, which I'm just going to put all together just for simplicity, we can introduce by RUP these constraints, which are literally just the encodings of these domains as equality literals. So it shouldn't be too hard to see that this is going to be RUP with respect to the original encoding. And then we can also introduce by RUP these 3 constraints for the values involved in our Hall set. So these are actually just taken directly from the all different encoding that I showed you before. So at most one of the variables can take this value, and all we've done is exclude the variables that don't exist because of the domain changes encoded in the reason. So now we've got a big load of PB constraints, 4 for the variables, 3 for the values. And now we're finally going to use cutting planes, and we're just going to add them all up. So as you can see, with all these positives and all these negatives, there's going to be a huge amount of cancellation. And when the dust settles, what we're left with is all those reasons conjoined together implies that minus B is equal to 1, which is actually enough already for a sufficient reason. But just because we like to be neat about things, we can also add in a literal axiom and add those together so we get reason implies obvious contradiction, which is exactly what we want. Peter's going to point out a mistake in this.
No, it's not a mistake, because the explaining all different would relax the domains of W, X, Y, and Z, and its explanation say all of the variables W, X, Y, and Z, as long as they take a value in 1 to 3, right, which is weaker than what we currently have, then the same explanation happens. Now, I'm sure you can just fill in the missing bits, and you'll still get the cancellation out, right?
Yeah. So actually, I mean, I've extracted that into the reasons, if you like, but we could just use for these 3 constraints, we could just use the model constraints because the remaining ones are guaranteed to propagate away. Yep. So this is kind of nice in a sense that it kind of depends where you want to put the responsibility for creating the reason. So when you add these things up in the proof, the reason sort of just falls out. But if you actually want to say, no, I want it to appear with this exact reason. So when we originally designed this procedure, we were using the sequence of guesses itself as the reason, which there are pros and cons of doing this from a proof logging perspective. But if you imagine this R is a G for the sequence of guesses, then that's why it's set out like this, because then you're guaranteed to get, in the end, guesses implies contradiction. But any reason implies contradiction will do, because all that we care about is that when we propagate the reverse unit propagation backtracking clause, that this propagates 0 equal 1, 0 greater than 1, and allows us to backtrack. So again, this is just to give a flavor. Yes?
So as I said,
And is this equivalent to just saying, look, I've got a set of inequalities and I'm just solving that there's an empty intersection, right? It's infeasible, this set of.
Yeah, well,
right?
it's
Which
kind
is-
of similar. So we thought about this in a particular way, which is that this set of inequalities is infeasible, obviously, and that what we've produced here, if you know about this, is like a Farcash certificate of infeasibility because we've added these up. The cool thing here is we actually use the information that our CP solver learned in order to do this efficiently. So if we didn't use the information, the whole set that came out of the CP solver, we would have to run the infeasibility question over all of the possible PB constraints that encode the whole all different deal with all of the variables. And we would get the same Farcash certificate out in the end. But we were running experiments and we submitted a paper to CP that's probably going to get rejected that showed this is not a great approach, to be honest. It's kind of slow compared to direct justifications. But nevertheless, that is effectively what this is doing, is just infeasibility of the LP, which happens to be totally unimodular, so it gives us a Farcash certificate. And so this explains why justifying all different is very nice. And there are various constraints which have similar sorts of arguments, in addition to all the constraints that can just be justified using RUP. So
can I ask
yeah.
a quick question just about the connection between what the propagator or the algorithm needs to output as its proof log and the representation as suitable in constraints that you use as the model. So do you need those two to be really synchronized? So does the propagator need to know what the representation in the...
So this depends how you want to implement proof logging. And this is like one of the kind of research questions that I've been working on while I'm here. So the way that we do it in the Glasgow constraint solver, which is our prototype implementation of this, is each propagator actually installs its own PB model into the proof when you start it. And at that point, it can pick any parts of the PB model that it wants to remember for doing proof logging. So in the all different, it will remember where these PB constraints are so that it can add them up. So that's a bit of bookkeeping.
I think my question is, from my point of view, if you wanted to start from a mini-zinc model, like you said in the beginning, you have this trusted component that has to basically translate the mini-zinc model into PB, but also into the input format for your solver, like flat zinc in that case, right? So I can see, I think what you're describing is if you start from flat zinc or whatever the input is to your solver, and then the solver generates the PB encoding of that. I can see how this, so is that's basically...
So that's what the Glasgow constraint solver does currently, but I don't think that needs to be the case because, and this is currently active ongoing research, but basically the solver can output a scaffold proof that is just the inferences without reference to any of the PB constraints that it needs to actually derive these justifications. And then we have an external justifier program that reads the PB encoding, which could be produced completely independently of the solver as well, and reads in the proof and then justifies each one with reference to that encoding.
So and you can guarantee that. Okay, so the solver basically just has to make an assumption about like the weakest possible way you could encode this constraint in PB, like, so that it's correct, and then produce.
The strength of the PB encoding will be a problem for the justifier. It won't be a problem for the solver, right? So the solver just writes out what it learned and then would go, okay, now you have to justify this in terms of PB. So this procedure that actually produces the justification needs to care about what the PB encoding actually is.
Yes, but the solver needs, but solver needs to kind of, like, if you want the system to work, the solver needs to output something
needs to be confident that we can justify everything. Yes. Okay. So if you used a constraint and you don't know what PB encoding I'm going to use, and you don't know if there's a justification procedure, you can't do proof logging. This is kind of the difficult challenge of this at this point. And actually kind of leads me very nicely to my next slide, which is going to be super laggy, or maybe not so super laggy, which is that there are many, many constraints in CP, and it is currently an open question whether all of them can be justified with nice efficient PB encodings like the ones that I showed you on the previous 2 slides. We have a lot of results so far in Glasgow that suggest that it's very likely that pretty much all, at least of the core constraints that standard solvers implement, because of course no solvers implement everything here, it's going to be easy to justify. But this doesn't tell us in general that there isn't some constraint hiding here that is actually like fundamentally hard for PB to justify in that sense. And that would be interesting to know. But in terms of where we are so far, if you implement these constraints in your solver, then I can tell you for certain that there are efficient PB justifications for all of these constraints, which are all pretty fundamental in terms of what a solver would implement. In my PhD, I've been looking at different families of constraints and trying to show in a kind of most general way what can and can't be justified efficiently. So I've got some results. So circuit is a little bit awkward, but very doable in PB. Bounds consistent multiplication is even more awkward. And we have published a paper at AAAI, which depending on how you look at it, shows that PB either is or isn't a good way to justify this. So it's the complexity of the justifications that we produce for that are n times m, where n and m are the number of bits used to encode x and y in the multiplication. So that's not great, although it kind of makes sense because PB is inherently linear and this is an inherently non-linear sort of constraint. So it is doable. It's not been an exponential blow up, but it's certainly a little bit of a pain, and it's something we might want to look at alternative justification methods for. Any constraint with an efficient smart table, someone took issue with the word efficient last time. Basically, I'm meaning a compact representation as a disjunction of conjunctions of constraints. Basically, if we know that we can represent the constraint in this way, then we can also proof log it in that way. Any constraint that can be efficiently, again, efficiently, I'm meaning compactly represented as an MDD. And in our most recent work, which is not published yet, but basically we're saying any constraint with a network flow propagator or a totally unimodular ILP relaxation, which explains why all different can be efficiently justified, along with a bunch of other constraints that effectively you're generating a far cache certificate to add up things with an infeasible ILP. I was going to put citations here, but if you're interested, I can show you the papers that have all of these results. But yeah, just to finish off, a slide disappeared there. There wasn't another slide, that's fine. There are lots still to do. So what I've been working here in the last 6 weeks are basically, we want to get to this stage where proof logging for CP is as easy as proof logging for SAT is, so that people actually implement it. Because we've done a lot of work in the Glasgow constraint solver to get our solver to output these PB justifications. And it's very clear that all solver authors are not going to do this. We're not at the very nice stage that we were at with DPLL or CDCL, where we just say, just write this all out and we'll handle it. We want to get to that stage with CP proof logging systems. Otherwise, there's no chance that everyone is going to implement it. Obviously, the encoding part is a barrier. It's a component of the system you have to trust. We've been collaborating with some people that know more about formal verification to construct formally verified PB encoding, so that this is no longer an Achilles heel of the system. And so far, we're relatively optimistic, again, because we're using very simple, straightforward PB encodings, that this should be doable, but it is not done yet, so that remains an open question. Another thing to point out is that counting and enumeration proofs are currently a completely open question. So VeryPB at the moment has no way of proving that this constraint problem has exactly this many solutions, or that you have found all the solutions. But it kind of has a way of proving all solutions, but it's a little bit theoretically unsound. But certainly this would be interesting. So we can do proofs of unsatisfiability, and we could do proofs of optimality. And of course, we can always witness satisfiable solutions. But these counting and enumeration arguments, there's been some interesting discussions on what these sorts of proof systems would have to look like. And this is an interesting open question. And in the meantime, for future PhD students at Glasgow, there will be more constraints to proof log. The fun thing about the Glasgow constraint solver is it is going to support all of the constraints, even the ones that nobody implements, because they're not really useful in practice, because we want to show that they are proof logging. So the big ones, disjunctive type scheduling and cumulative scheduling type propagators we've not done yet. We have ideas that these are probably okay to justify in various ways. Peter's raising his eyebrows. And there was actually a PhD application to think about doing this, but it's yeah, currently still an open question. So there's lots of interesting, exciting research directions to take this in, and we really hope that in a couple of years' time there will be a certified track in the MiniZinc challenge, and that more CP solvers will be producing proof logs and being trustworthy automated theorem provers. So there's some links if you want to scan links. I just put them on because there's more space in the slides. But that's all I have to say. I don't know. Yeah, that's time, I think.